here's a system, just a basic booster system, and let's plot it. And this is how, when I'm doing a training and I'm talking to the technicians, is getting them to understand how does that really work. Because their PNIDs are going to look a little bit different than this, but you can plot the PNID right on this chart and putting the numbers in. I think that's been the game changer for me from learning design and engineering on CO2 systems, is plotting all these numbers. And when you can plot all these numbers where they're at, you can understand how to troubleshoot a system way faster. I've seen technicians come into my supermarket and CO2 programs and start plotting the numbers for both voltage and both pressures and temperatures. And they're like, this makes so much more sense. This is why this three-way ball valve is switching. It's not to do with anything but temperatures or pressures or voltages, and understanding how to plot it. So let's do this quick example here. Once again, so here's our transcritical compressor. I got here on here a Bach compressor. It could be anybody's compressors. But what happens? That energy comes in, that starts up that compressor. So you get energy there. So it starts moving those pistons up and down. We know this. But as it starts to compress it, then we have de-superheating gas starting to go up that discharge line that goes out to either, in this one, we don't have any heat reclaim or heat recovery. It's going straight out to that gas cooler at this time, because we know right now we're above the critical point. We are in transcritical. This is a supercritical fluid going up to that gas cooler. Now, this gas cooler at this point, we know is just cooling the gas. It's just pulling out as much heat as possible to get us closer to the condensing point, because we can't get to condensing because we're above the 2 points, the critical pressure and critical temperature. We're above that critical point. So what we're doing, we're cooling it down as much as possible. So when we go through that high pressure valve, when that fluid hits that high pressure valve, that we have as much liquid in that vapor as possible, or the least amount of flash gas as possible coming through that valve, which is so, so important. Because the less flash gas we have in there will mean, when we're coming through this high pressure valve, the less flash gas we have coming in will mean the less flash gas, in this example, going back through that transcritical compressor. And this here is key to understand. Is like, I have conversations like, well, what causes that compressor to work harder? Well, it's pressure ratio. That's it. Pressure ratio. The bigger the pressure ratio, the more work that compressor is going to do, the more heat that stator is going to do. It's pressure ratio or compression ratio. Depending on where you're at in the world, you'll call it differently. But as that pressure ratio increases, it gets bigger. It's just more work. More work for those compressors. More work leads to more energy. More energy leads to higher cost. And if it's too much work, and if it's overwork, that means that now we're working the compressor in real hard to the point where now over time it's reducing the life. Instead of those 10, 15, 20 years, 5 years or 6 years getting out of that, because we're working the compressor too hard. And you want to make sure, is it this too much flash gas working? What do we need to do? That's why there's designers designing systems, especially in our design program. I've seen designers winning projects now on changing up the way they do their design. So maybe when they're doing a design, they're adding a plate heat exchanger on the drop plate to get more to get that temperature, get actually liquid getting to this valve, or adiabatic cooling, or parallel compression. There's lots of different strategies that are out there, and I'm seeing it from the designers in the course doing different approaches, coming up with different things to try to make sure we get the least amount of flash gas going into that receiver. And as we get into this receiver, because it is a receiver, we call it a flash tank. Some people call it a vessel. Some people call it the receiver. To me, it doesn't matter. Whatever terms you use, just make sure when you're talking to someone, if you're talking to the end user, you're talking to the manufacturer, you're talking to the engineering firm, or you're talking to the contractor technician, use the same terms. That's a big, big deal. Because I've had conversations and lots of conversations in our CO2 training programs where they're using different terms. Like some people used to call this the magic valve for years. It's not a magic valve. It's a high pressure valve. It's a pressure regulating valve. What it does, it allows flow through it. That's all. When you can, it's a restriction in the pipe. My good friend Kevin Mullis from the UK, he's like, that was multiple times on the podcast. He said it's just a restriction in the pipe, and that's all it is. When you can get your head around that, that's a restriction in the pipe. We're opening and closing, trying to change the flow of that. It makes a huge deal. So we get into here, and then what we have, I already talked about, we got the flash gas going here. As we change the pressure in this flash tank receiver, as it goes up or down, the pressure will change where it hits on this line here. So it will change, and when it comes down, that's going to be a different amount of flash gas in there. So as that, and if you go into the Danfoss Cool Selector 2, I know I talked about it a lot. We use it in the design program, even in my CO2 training programs with technicians. I use it to show them how it changes that mass flow of that vapor or that flash gas going in there. So as you change that vessel pressure, that flash tank pressure, receiver pressure, it's going to change the amount of work that this valve is doing. And then that means if there's more flash gas going through or less flash, it's going to change the amount of work on these compressors right here. That's a big deal, because that's such a big deal. It's because now it's costing the customer more money. Maybe if you're a technician, maybe that doesn't matter to you. I just need it up and running and need to be cold, and no problem. That is great, and I am with you 100%. But those of you that can fine tune that system and get that system running as top notch as you can, that's the game changer. That's the technician that is a game changer. And I see this in lots of our training programs, technicians going out there, going above and beyond what it needs to be done on these CO2 systems, and learning a little bit more, getting into the PNID, getting into the controller, getting into the electrical wiring diagram, and understanding how to plot it. And that's where the game changer is. Because I see multiple times technicians come into the program and like, I kind of understand the sequence of operation. Well, no, let's understand. There's no kind of. Let's understand exactly the way that's supposed to work, so you understand when a problem happens. I have an oil issue because that receiver is going up and down. The temperature is going up and down, or the pressure, however you want to call it. That pressure goes up and then it goes down. It goes up and it goes down. That is going to change the effect on a certain design. So if you're using a oil receiver or oil vessel pressure, so you're running your receiver at the flash tank pressure, your flash tank's all over the place. What is happening in that receiver? That oil reservoir, okay, it's all over the place. Things to consider, okay? And then when we leave out, one great thing about this is when we leave out this receiver, this flash tank, this vessel, we're sending liquid, good quality, hopefully good temperature, liquid out to all those metering devices. Their electronic valve doesn't matter. It's electronic valve. It shouldn't matter to you if it's electronic valve, if it's a TX valve, a piston valve. It shouldn't matter. If you're out in the field, if you're designing it as a designer, or if you're a technician in the field, it's just another restriction. We're dropping the pressure, and we drop the pressure because we know we need to drop the temperature. And this is all the electronic valves are doing. So what we're doing here is we're dropping the temperature to 1 point. So we get we're pulling the heat out. We're actually dropping the temperature to remove heat. So using that CO2 to actually absorb the heat, to make sure that we can reject it out into the atmosphere, which I love that we're learning the ways to reuse that heat in heat recovery and heat reclaim, and not just rejecting it out to the atmosphere. So we're coming up with better efficiency strategies. I see tons of different models out there. I'm seeing some now where they're keeping the systems in subcritical at all times, which is amazing. If you can keep this system in subcritical at all time, it's going to be way more efficient than if you're running in transcritical all the time. So that's the goal, to keep it below transcritical, so you have liquid coming down the drop leg, not fluid down the drop leg. Okay, so, and then right here, we push out a little further. What does that really mean? So in this example, we must have a subcooler in here. We're pushing that out a little further. So when we drop our temperature down for our low temp to remove that heat, that we are actually removing the proper amount of heat of that product that's in those display case, coffin cases, as we can see here. And then we're now taking it back to that booster compressor. That booster compressor now is compressing it and taking that heat and now moving it into your transcritical compressor. And I know this is all CO2 101 information, but these key terms and these key words are so important. So really want to visualize it. So if you're driving your truck now and you're just listening, kind of visualize how that's going through the system. And this is where the turning point for me in refrigeration it was with CO2 systems, but I couldn't see inside the pipe. I could get the pressures and temperature, but I couldn't really visualize what's actually happening in that pipe. Now I can. I can see if there's going through this discharge line. What is it? It's actually a fluid there when we're above that critical point. It's a fluid going up. There's actually a fluid coming down here. When we come here, I can visualize flash gas coming out of there. I can visualize that. And I can visualize now the amount, like how much is coming through there. It all depends on where you're at in this enthalpy diagram. So the more you can visualize that, we know right here, this should be liquid, good quality, good temperature, good stable liquid. Because when we're stable, we got a stable suction. We got a stable discharge or head pressure. We got a stable receiver pressure. We got stable evaporators. Man, that system will just purr and it just will work. So systems that are designed correctly, they're installed properly, they're serviced and they're started up and commissioned properly, and then they're serviced and maintained properly. Nobody has issues with them. I talk with people that the system's been running for years, and all they've done is their simple 6 or 1 year maintenance. That is it. It just works. It just works. But that is where I see the design firm, like the designers that come into our design program, they are working closely with the contractor as well as the manufacturer, as well as the end user. And that's where I see the best CO2 systems coming out there. And it's not where it's just two parties. It has to be all the parties working together for the best systems. And I see this starting to go away a lot more, but I know the designers that we're working with, the technicians I'm working with, I'm trying to get them involved. So it's a team effort. And when there's a team involved in building these CO2 systems, everything's working a lot better, hands down. And I see it all around the world with the people I'm working with. The systems that have issues that I see, there's one or two parties left out. One or two parties left out. And it could be anyone. It could be the retailer left out. It could be the contractor left out. It could be the manufacturer left out. When you have all the 3 parties, 4 parties involved, it's a game changer for that system. They work. They work. And the ones that aren't like that, there's issues over time. And I've consistently seen this. Hopefully you enjoyed this and took a few things away. Like, share this with other people. Like, if you think this was valuable for you, it's going to be definitely valuable for somebody else. This is the way I see it. And the way I see it is that understanding the thermodynamics, understanding the design, understanding engineer, understanding the install, understanding the startup commissioning, understanding the service is where you differentiate yourself from the rest of the pack. And this goes for designers, this goes for technician, this goes even for the retailers, the refrigeration leads on that. Those of you that are putting the work in today are benefiting tomorrow, because I see this in our CO2 design course. I see this in our CO2 intro course. I see this in our CO2 advanced course. Those putting the work in, they are skyrocketing. They are leveling up into companies. They are running companies now. They are actually getting better positions. They're getting more money. They're getting new roles. There's so much going on when you put the work in. And this is why we're here today. I want to thank you for taking the time to come out and just learn a little bit about keywords and terminology. There's a lot more to it. This is a high level of CO2 keywords and terminology. And I appreciate you taking the time to listen. So please share this. If you're listening on the podcast or if you're watching on the channel, YouTube channel, please share this with others. We're here to uplift the industry by helping each other. That's what we do here at Refrigeration Mentor. We're helping people all around the world to level up. So if you're interested in one of our programs, reach out to me. Send me a message, send me an email, trevor@refrigerationmentor.com, and one of my team members, or jump on a call with me. That would probably be the best. Jump on a call with me and see how I can design a program that's going to level you up. Because definitely the contractors that are taking advantage of this and leveling up their technicians, they are not getting, those lead technicians are not getting as many calls. Those service managers like Trevor are just not getting these calls anymore that I used to. How do I charge the system? Or how do I change the oil separator in a CO2 system? Or how do I change the liquid line filter dryer? How do I do an oil sample? All this stuff, you don't have to get those calls anymore. And this is what we're doing, helping the industry out, diving into this stuff deep. I want to thank you for taking the time to listen. So look forward to seeing that more refrigeration mentor training programs, webinars. Appreciate you all. Level yourself up, help the people around you as well. And always let's get a conversation going. Thanks, everyone.